Okay, so this is the first podcast of Unit 3, and we're actually going to skip over that little bit of history. We're going to find a way to do that in class, but we're going to start by jumping into the basics of the periodic table and then focus on our very first periodic table trend, a pattern that we're going to be using to predict some properties throughout this unit. So let's jump right on in. You've got a little bitty periodic table there in the middle of your packet, that first page of your packet, and I want you to go ahead and draw a stair step into that periodic table. There is one in the printed periodic table that I've already given you, but I want you to add this one and make it bold, make it stand out, because that is one of the most important things in this periodic table. And that staircase is the dividing line between our metals, which is everything to the left of that staircase, and our non-metal section, which is everything to the right, kind of above that staircase. The one exception is hydrogen. Hydrogen is a non-metal, but it's over in that first column for valence electron reasons. And on top of those kind of simple dividing lines there with that staircase, we have several different groups of elements that have similar properties that we need to start learning some of the names for so we can identify these groups and talk about their shared properties. So the groups we're going to be talking about are all columns on the periodic table. And that's a word you should also kind of familiarize yourself with. Is groups is another word for columns, and periods are another word for rows. So it's important we start to get familiar with that terminology because I'm going to use it some, and that means you need to be able to understand what am I even talking about. And there's one more special group area that I want to talk about. So go ahead and add this transition metals right there underneath the noble gases section in your packet. And let's go over where are all of these groups. Well, our alkali metals are in group 1, column 1 of the periodic table. If you remember from Unit 2, that means they have one valence electron, and according to the octet rule, they could lose that one valence electron to get happy and stable. And because it's just one electron they've got to lose, they're going to be pretty aggressive about losing it. So those alkali metals have some of the highest reactivity out of all of the elements on the periodic table. The alkaline earth metals are in the second column, and these two names for these first two columns are very similar, but what I remember is there's one special name for the metals in the first column, and there's two names for the elements in that second column. You've got to be able to tell those apart. They have two valence electrons, so they would have to lose two electrons in order to get happy and stable according to the octet rule, which still isn't much. They're still pretty high reactivity, but not as high as those alkali metals because it takes them longer to make that change happen. Then our halogen group is actually all the way across. It's the second to last column on the periodic table, and if you count them, it is 17 columns over. And they have 7 valence electrons, so they just need to gain 1 according to that octet rule to be happy and stable, which means kind of like those alkali metals, they're going to have very high reactivity. And it's kind of hard to compare these metals with these non-metals reactivity, but they're both going to be the most reactive groups of their specific kind of areas. Then our noble gases, we've already talked about those a little bit, are that last column, column 18 on the periodic table. And because they already have 8 valence electrons, they're happy. They don't want to gain or lose any electrons. So they have the lowest reactivity out of all elements on the periodic table. We even call them inert gases, meaning they don't react. They are going to actively avoid reacting with other elements because they don't want to gain or lose electrons. Now, the transition metals are kind of this D block area, columns 3 through 12 in this middle area. It also technically applies to these metals that are underneath the staircase. So this whole area, including some elements that are in boron, carbon, nitrogen, and oxygen's column, but they're metals, so they don't go with those non-metal groups. And because these are in the middle of the periodic table, no matter whether they gain or lose electrons, they've got a long way to go to getting happy with that octet rule, which means they tend to have fairly low reactivity. So just a little reminder of how these blocks kind of break down into those metals and non-metals there. And really when it comes down to it, we need you to be able to find an element and find some information about that specific element. These are all the things we should be able to find and identify about our element. So I'm going to do this first row with you. If we look at the periodic table at the element that is at helium 2s2 2p5, you'll find that that's fluorine. And that fluorine is over there in that P block area, and it is in the second row of the periodic table, which is another word for period. So it's in the second period of the periodic table. And because that's that second to last group over there, that's group 17. And like we just wrote above, group 17 are called the halogens. And type of element is metal or non-metal. And this specific element is a non-metal. And reactivity, we said that those halogens have very high reactivity. They're the highest of our nonmetals, but very high works too. So I want you to try to fill in the rest by yourself. There is this little typo, well, technically two typos. That 3 at the end of that second to last row should be a little superscript there. And instead of 4p2 down in that last row, it should be 4f2 there. And because that's an F, you're actually not going to have a special group or group name. It's not really in those areas we just talked about above. So you're not going to be able to fill in these 3 spaces, but you should be able to fill in everything else there in that last row. So you're not going to see a table like that on the test, but we will give you several questions where we just ask you, find the element in the periodic table that has certain properties, like what's the alkaline earth metal that's in the 5th period? Well, 5th period means 5th row. Alkaline earth metal is a second column. And if you look at the periodic table, if we count 1, 2, 3, 4, 5 rows down, second column, well, that's strontium. So we're going to practice with these a lot, and it might seem like some random facts, but we're going to be putting those facts together to find specific elements. It might not always be groups and periods, but it could be. You could also ask you about valence electrons. Any of these properties that we know about these groups and these rows could help us identify an element. So we'll practice with some of those in our bell ringer when I see you next class. Now, at the top of the next page, we're going to get started with our first real periodic table trend and the reasons for all of the trends. And we're going to learn 5 different trends in this unit. The reason why everything happens this unit comes back to these 2 words, shielding effect and nuclear charge. So we're going to define them here, and I'm going to keep revisiting them every time we talk about a new trend, but it's important you understand these 2 words to understanding what's happening and why it's happening in the rest of the unit. We're actually going to start with nuclear charge. It's exactly what it sounds like, the charge of the nucleus, which is going to be equal to the number of protons in that nucleus, because the only other thing in the nucleus are neutrons, and they don't have a charge. And this nuclear charge is going to increase as we go from left to right in the rows of the periodic table, because as we go from left to right, that atomic number gets bigger, which means our overall nuclear charge for our elements get bigger. Now, that seems pretty obvious, and you might also think that the nuclear charge increases as we go down, but it doesn't, even though that atomic number gets bigger. I'm going to show you in a minute why the effective nuclear charge is actually the same even as we go down the periodic table. And that actually comes back to the shielding effect. Shielding effect is the effect caused by inner energy levels of electrons canceling out part of the nuclear charge for the outer electrons. They're acting like a shield, protecting those outer electrons from the pull of the nucleus. And this is going to increase as we go down in any column of the periodic table, because as we go down, we're adding energy levels, which is adding those layers of protection to those outermost electrons. So let me help make this a little bit more clear for you with this example. It's not in your packet, but I wanted to just compare 2 simple atoms, hydrogen and lithium, and they are right by each other. Hydrogen is right above lithium in the periodic table. Hydrogen's element 1, so it has 1 proton and 1 electron just to start with. Lithium has 3 protons and 3 electrons. But because lithium has 2 electrons in this inner first energy level. That's their 1s2 electrons, and then they have the 2s1. These inner electrons are shielding and protecting, kind of canceling out two of the positive charges from that nucleus. So when the nucleus is pulling on that outermost electron, it's not feeling the full pull of the nucleus, not like this hydrogen electron is. It has no protection. It's going to feel the pull of the full nucleus's charge, which is just one proton, so positive 1. Lithium's outermost electron also feels an effective nuclear charge of 1 because 2 electrons here are canceling out 2 of those protons, which just leaves 1 proton's worth of charge that makes it through that shielding to get to that outermost electron. So as we go down a row, we're adding these circles around the atom. We're adding shielding, and that shielding is causing the nuclear charge to effectively stay the same. So we'll talk about that more as we focus on this atomic radius trend. Now, I know there's a periodic table right above where we're writing the definitions for these things, but I want you to jump down under the periodic table for a minute. Once we finish writing down some definitions and understanding what's going on here, we can jump back up top and draw some things on that periodic table. So, our atomic radius is the average distance from the center of the nucleus to the edge of the electron cloud. It's a radius of an atom. It's the definition of a radius with atom words shoved in there. Really what this tells us is the size of an atom. So if I ask you which atom is larger, it's going to be the atomic radius that tells us that. Now, if we think about why our atom would get bigger and smaller, the why always comes back to those 2 words we just explained. So let's talk about the nuclear charge. Remember that that's increasing as we go across a row because we're adding more protons. So this is kind of the base explanation of what's going on here. Because that increasing nuclear charge is pulling harder on the same energy level of electrons and getting pulled in closer to the nucleus, that means the atomic radius will decrease. And if we're talking about shielding effect, as we go down that group, down a column, we get more and more of those energy levels of the atom. Well, because we're adding electrons to higher energy levels, the atom gets larger. Those bigger circles are just getting bigger and bigger. Each one we add is going to make our overall atom larger. So, more energy levels, larger radius. So, if we put these together, when we look at that periodic table there, we said that the atomic radius decreases as we go from left to right. So if we're going to draw an arrow to show where our biggest atoms are on any row, I would encourage you, draw the arrow from right to left. Make it point towards the left. That's going to be where we find our biggest atomic radii on any row, is at the far left of the row. And we said that atoms' atomic radius gets bigger as we go down. So let's also draw an arrow down next to that periodic table. So in any column, the biggest atoms are going to be at the bottom of the column. And if we put both of these arrows together, we end up kind of pointing towards the farthest left and the farthest down atom, francium. That is the largest atomic radius on the whole periodic table. And go ahead and circle it, star it, or write down this little side note that because francium has the greatest atomic radius out of every element on the periodic table, when we're answering questions about atomic radius, the closer those elements are to francium, the larger their atomic radius is going to be. So this is kind of our trick. We don't have to memorize all those complicated definitions and reasonings. If we can compare the position of our atoms to francium, we can figure out which one is biggest. So let's do that in a couple of examples down here. I've got my francium highlighted red so we can still see it here. And in each set of problems, I'm going to highlight the elements it's asking about. So here with lithium versus fluorine, which one is closer to francium is going to be the one with the larger atomic radius. And hopefully you agree that lithium is much closer to francium than fluorine is. It's way, way farther away. So lithium is our larger atomic radius. With these next two, SR or SN, well, SR is also way closer to francium, so it has the larger atomic radius. Sodium and rubidium are in the same column, so we could just focus on that vertical trend, but francium helps us with that too. Rubidium is definitely farther down, closer to francium, so it has the larger atomic radius. Now, we might not just be asking which one is the biggest. We could also ask you to arrange them in order. And the thing to be careful about with this increasing order is that increasing means smallest to largest. When we're writing them in this order, it needs to be getting bigger, increasing in size. So increasing means start at the smallest and go to the largest. So cadmium, because it's farthest away, is the smallest, and we're just going to be working our way back towards francium to get that increasing size. So our order is going to be CD, TC, and then Y. Half the battle for this is just finding those elements, but in class I'll let you use a dry erase marker on those periodic tables to help find them and get them in order. Once you got that, then it's easy. Looking at this next set of elements, they're all in the same column, and if we're focusing on increasing size, farthest to closest was going to get us our biggest to smallest, smallest to biggest is the order. And hey, look at that. It just so happens to be the exact same order they were written in. You might not guess that if you were just guessing on a test, but it could happen. And looking at these last three elements, they're way far away from francium, but that doesn't even matter because we can still see that the farthest one is Xe, and as we're getting closer and closer, that's going to make them larger. So Xe, I, and then Te is our increasing size for those elements. So I put all of those examples back up just to make sure you got those down, because we're going to learn about another trend in class, and it's going to follow the same kind of general idea. Find which element is the biggest for that pattern, for that trend. Closer is bigger, farther is smaller. So come with questions in class and be ready to do some activities to fill in the rest of a couple of pages.